Welcome to a slow, beginner-friendly lesson on what hashing is and why it matters, made for absolute beginners. The first tool of protection. You spent the last few lessons storing data, users, orders, emails. Today we cross from storing to protecting. The first tool in that direction is hashing. A hash is a fingerprint for data. You feed in any input, however large or small, and you get back a fixed size fingerprint that uniquely identifies that input. Same input always gives the same fingerprint. 1 byte different, completely different fingerprint. And crucially, you cannot reverse the process. In this lesson you learn what hashing is, what it is not, the 4 properties that make it useful, and the real places it shows up in everyday software. A fingerprint for data. Here is the bridge from the last lessons to this one. You stored user data. Names, emails, orders, amounts. But storing is only the start of the story. Some data must be protected even when it sits quietly on disk. Passwords, for example, should never be stored as plain text. File contents should be checkable for tampering. Hashing is the first tool that makes both possible. Today you meet it as a concept, no library details yet. From storing to protecting. You stored user data. Now a harder question, how do you protect it, even from yourself? The vault is open. A hash is a function. It takes any input you give it, however small or huge, and returns a fixed size string of characters. That string is called the hash, or the digest, or the fingerprint. The same input always produces the same output, every single time, on every machine. And the smallest possible change to the input flips completely changes the output. Hashing is a one-way fingerprint for whatever data you feed in. Same input, same fingerprint. Hashing is not encryption, and the difference matters. Encryption hides data, but it can be reversed with the right key. You can decrypt an encrypted message and get the original back. Hashing cannot be reversed. There is no key. There is no unhash function. A hash is a fingerprint, not a locked box. You use encryption when you need to recover the original later. You use hashing when you only need to verify that something matches. Not encryption. Picture the core idea. Any input flows into the hash function. Out comes a fixed length fingerprint. Feed in the word hello, get a fingerprint. Feed in the word hello again, get the same fingerprint, character for character. Feed in hello with one letter changed, and you get a completely different fingerprint, with no visible relationship to the first. The function is deterministic and unpredictable at the same time. Input in, fingerprint out. A hash is a fingerprint for data. Same input, same fingerprint. Lose 1 byte, the fingerprint changes completely. Quietly unique. The first property is deterministic. Given the same input, the hash function always returns the same output. On your laptop, on a server in another country, in 10 years' time, the same input always produces the same hash. This is what makes hashes useful for verification. 2 people on opposite sides of the world can hash the same file and compare fingerprints. If the fingerprints match, the files match. Reproducible everywhere. The second property is one way. You can compute the hash from the input easily. You cannot compute the input from the hash. There is no unhash function. The output simply does not contain enough information to recover the input. This is exactly why hashes are used to protect passwords. The system stores the hash, never the password. Even if an attacker steals the hash, they cannot turn it back into the password. No unhash function. The third property is fixed size. Whatever size input you feed in, the output is always the same length. A 2-byte input produces the same length hash as a 2 GB input. The common algorithm SHA-256 always returns 64 hexadecimal characters, no matter what you feed it. Fixed size makes hashes easy to store, easy to compare, and easy to index. Always the same length. The fourth property is collision resistance. It should be extremely hard to find 2 different inputs that produce the same hash. With a strong algorithm like SHA-256, finding a collision would take billions of years on the world's fastest computers. This is what lets you trust a hash as a unique identifier. If 2 hashes match, you can be confident the inputs match. If they differ, the inputs differ. Unique in practice. Put the 4 properties together and you see why hashing is so useful. Deterministic means anyone can reproduce the same fingerprint. One way means an attacker who steals the fingerprint cannot turn it back into the data. Fixed size means fingerprints are easy to store and compare. Collision resistant means a matching fingerprint truly means matching data. 4 small properties, 1 powerful tool. 4 properties, 1 tool. You can compute the fingerprint in a heartbeat. You cannot reverse it back to the original. That is the whole point. One direction only. Here is hashing in Python. You import hashlib, part of the standard library. Call hashlib.sha256 with the bytes version of your input. Notice the B in front of the string, which means bytes, not text. The hash object has a method called hexdigest that returns the fingerprint as a string of hexadecimal characters. That long string is the fingerprint. 64 characters, every time, for any input. Hashlib ships with Python. Watch determinism in action. Hash hello once, get a fingerprint starting with 2CF24DBA. Hash hello again, get the exact same fingerprint. Hash it 1,000 times, same answer every time. This is the property that lets two people on different machines compare fingerprints and trust a match. If their hashes agree, their inputs agree. Identical every time. Now watch what happens with one tiny change. Hash lowercase hello. Then hash capital H hello. Only one letter differs. But the fingerprints are completely different. No visible relationship between them. This is the avalanche effect, and it is what makes hashes collision resistant. An attacker cannot tweak an input until the hash matches another. Each tiny change scrambles the whole output. Avalanche in action. Watch the fixed size property. Hash a tiny input, just the two letters HI. You get 64 hex characters. Now hash a huge input, the same letters repeated 1,000,000 times. You still get 64 hex characters. The output length never changes, no matter the input size. That is why hashes are easy to store and index. The biggest file on disk still produces a small, fixed fingerprint. 2 bytes or 2 gigabytes. Two methods give you the hash back. Digest returns the raw bytes. Hexdigest returns the same bytes as a printable hexadecimal string. Most of the time you want hexdigest because you can print it, store it as text, and compare it with another hash stored the same way. Use digest only when you specifically need raw bytes, for example when feeding a hash into another cryptographic function. Hex is printable, bytes are raw. File integrity, password storage, deduplication, blockchains. Hashing is quietly everywhere in modern software. Used everywhere. First real use, file integrity. When you download a large file, the publisher often publishes its hash alongside it. You hash the downloaded file on your machine. If your hash matches the published one, you know the file was not corrupted and not tampered with during download. Linux distributions, software installers, firmware updates, all rely on this. One small fingerprint, total confidence that the bytes are correct. Has this file changed? Second real use, passwords. When a user creates an account, you hash their password and store the hash, never the plain text. On login, you hash the password they typed and compare the two hashes. If they match, the password was correct. If an attacker steals the database, they get a list of hashes, which they cannot reverse back into passwords. This is why every reputable site stores passwords only as hashes. Never store plain text. Third real use, deduplication. To find duplicate files, you do not compare entire files byte by byte. You hash each file once and compare hashes. Matching hashes means matching content. Backup tools use this to skip files they have already saved. Git uses it to identify commits and trees. Cloud storage uses it to store one copy of an identical file uploaded by many users. Hashes turn huge comparisons into tiny ones. Have I seen this before? Hold these 4 ideas. A hash is a one-way fingerprint for data. The same input always produces the same fingerprint. A tiny change to the input produces a totally different fingerprint. And you cannot reverse a fingerprint back into the input. That combination of properties is why hashing is used for file integrity, password storage, and deduplication all over modern software. The first tool of protection. The fingerprint you can trust. Quick self-check. Can you explain in one sentence what a hash is? Can you say why hashing is not the same as encryption? Can you name the 4 key properties? Can you list 3 real places hashing shows up in everyday software? If any of these feels shaky, rewatch the matching part. This is the foundation of every protection technique that comes after. Say each out loud. Storing data is the start. Protecting it is the rest. Hashing is the first tool in that direction. Protection begins. This is the close of phase of point 8, and the close of the whole foundation. You can store data, change it, remove it. You can keep queries safe with parameters. You can join data across tables. And you can hash data to fingerprint it. From here, the road opens up. Web apps, command line tools, cloud scripts, automation, AI workloads. All of it rests on what you now know. The foundation is complete. The real work begins. The foundation is complete. Thanks for meeting hashing, the first tool of data protection. The foundation is complete. Protection begins.